right, thank you very much. Is this working? It's working. Okay, great. So we all had some workout. I think we're all back and energized again. So many talks about Manjul's mathematical works, about its significance, about how it changed certain fields, how we view, for example, geometry of numbers. I think much can also be said about his exceptional expository skills. I don't think I'm senior enough to say more about that, but I would just say that when I was a graduate student of DIC, that's when I first met Manjul. And in DIC's talk, I always get this feeling that, man, this thing is totally awesome. But when I go to Manjul's talk, it's more like, why am I not working on this? So I'm honored to say that in this case, I am working on this, and I hope you will find this also being totally awesome. Okay, so I want to report on this joint work with Manjul and Arul on square-free discriminants. Okay, so let me begin by recalling what discriminant is. If you start with a degree n polynomial, okay, then you can define the discriminant by taking the product of the squares, the difference of the roots, or you can define it as the resultant of f its derivative. If you're only working with monic polynomials, then that's it, right? But if you want to work in the general case, you have to modify by the leading coefficient a little bit. So in the end, you will get a polynomial in the coefficients of f with integer coefficients. It's homogeneous of degree 2n minus 2. It's also irreducible. Sometimes it's more convenient to think of the discriminant as being weighted homogeneous. If you give each ai degree I, then it's weighted homogeneous of degree n times n minus 1. So that's like giving each root degree 1 and then giving a naught degree 0. Okay. So here are some examples. For degree 2, you're looking at squared minus 4ac. Okay, that's degree 2 homogeneous and weighted homogeneous. For degree 3, you get this quartic in 4 variables. I took this formula from Wikipedia, so I'm pretty sure it's correct. All right, so what's the main question? The main question is, if you start with a random polynomial, what's the probability that its discriminant is square-free? Okay, so in many of the talks, we have an infinite family, infinite number of elements. What does it mean to talk about the proportion? Right, you have to order them somehow, and we just order them by the most naive ordering, by the maximum of the coefficients. So if you look at this box of integers n plus 1 tuples of size x, and you ask for the proportion of them that have square-free discriminant, okay, and then you take a limit as x goes to infinity, the question is, does the limit exist? And if it does, what is its value? In this talk, I will be focusing primarily on monic polynomials. Right, so those are the cases where a naught is actually 1. And in that case, it's more convenient to think of the discriminant as being weighted homogeneous. Okay. Degree I, and then I will be looking at a skewed box where each ai can go up to xzi and ask for the proportion and then a limit. Okay. All right. So before proving anything, you can make an educated guess. Right? So what does it mean to say an integer is square-free? It means it's not a multiple p squared for every prime p. Okay? Well, it's kind of hard to do it for all primes at the same time, so let's do it one prime at a time. For each prime, I can define this probability, lambda p, that the discriminant is square-free at p. Okay? That's just, you allow the coefficients to vary in z mod p squared z, and you ask for this proportion where the discriminant is non-zero. Okay, so that's the probability that it's square-free at p. And then you hope that some version of the infinite Chinese remainder theorem, some infinite version of the Chinese remainder theorem work, right? So these conditions at different primes, hopefully they are independent, right? So then if you take the product, I should give you the density where it's square-free everywhere. Okay. What's wrong with this? There is no infinite version of the Chinese remainder theorem. You can only apply it to finite many primes at the same time. So you can apply it to all primes less than some fixed m. Right? So you count the number of polynomials where the discriminant is square-free for all primes up to m. Okay? That's going to give you the product over all primes less than m of the lambda p, and then you take limit as m goes to infinity. Okay? So that immediately gives you, immediately proves that this product is the upper bound. The hard part is to show that this is also the lower bound, and that's what I'm going to be spending the rest of this talk on, so proving this lower bound. Okay, some motivations about why people care about square-free discriminant. I mean, this is a number theory audience. I don't really need to say much about this. if you take an irreducible polynomial with square-free discriminant, then two very nice properties hold. The first is if you look at the field generated by F, this degree n field, then the Galois closure has Galois group Sn, the full symmetric group. I'll probably assign this as a homework problem to my Algebra 1 student this term. And then the second property is easier, namely, you know what the ring of integer is. Right? It's given by Zx mod f of x. In particular, it's generated by the image of x. So this is what we call a monogenic Sn field. Right, so then you would think that, you would be right, that knowing the correct proportion of polynomials with square-free discriminant should tell you something about the number of monogenic Sn fields. Well, as interesting as it is, that's not how we got into this problem. We were primarily interested in Selmer averages. And Dick mentioned one result in his talk very quickly, which was that the average two-Selmer size of the two-Selmer set of J1 was bounded above by 2. If you want to prove that it's actually equal to 2, then it basically reduces to one of these square-free sieves. So that's how we actually got to this problem. Okay, so what's the main theorem? The main theorem is that the educated guess is correct. That's always a good thing when when the most natural thing works. So if you want to count the number of integer polynomials, monic integer polynomials having square-free discriminant, then it's exactly this Euler product. Arul will say more about the case of general polynomials in his talk. So in this case, just monic. What are these local densities? Well, they have been computed by Brackenhoff. Very nice formula. They depend on n, but as n goes to infinity, they will approach 35.82%, the product. Okay, so that's one thing you can ask. Another thing you can ask is, how often is Zx mod f of x the maximal order in Qx mod f of x? Of course, if the discriminant is square-free, then this is immediately maximal, but that's not necessary. And it turns out that this proportion also exists, this density also exists, and it's 6 over pi squared, the product of 1 minus 1 over p squared. This density was computed by Lenstra. Okay, and then finally on the matter of monogenic Sn fields, we were able to prove that also, I guess, there's some constant times x to the 1/2 plus 1 over n of these monogenic Sn fields of discriminant bounded by x. So degree n number fields with Galois group Sn in the Galois closure, and whose ring of integer is generated by one element. So I'll be talking more about the first theorem, and then the second theorem will actually follow from the proof quite immediately, and then I probably won't have time to talk about the last theorem, but the general idea is it turns out that 100% of these polynomial will give distinct rings. If you just look at Zx f of x, they will usually be distinct. And we distinguish them by viewing them as lattices in Rn. And Piper will speak more about this shape of the lattice tomorrow. And then we use our result on square-free discriminant to say that if we know that these rings are distinct, then being the ring of integers, that also tells you that the fields are distinct. Yes?
So if we only were looking for degree n number fields with Galois group Sn, then the expectation would be that it's O of n.
Yes.
Is that still the correct expectation when we also insist that they be monogenic?
Yes, we believe this is the correct order of magnitude. Yeah. And we also have a guess on what the constant should be.
The x to the 1.
Oh, that actually, where you were.
When it's monogenic.
For monogenic, it should be 1/2. Yeah. Well, we think. Yeah. Any other questions? Comments? Protestations? Okay, so I want to focus on the first theorem. Talking about that, let me step back a little bit and look at a more general problem. And so the case of polynomial discriminant is the case where you start with a polynomial delta n, and then you ask for how often it takes a square-free value. So instead, we can also just start with any polynomial and ask the same question. So more precisely, you look at n tuple integers in a box and ask for the proportion of them where the value of f is square-free. Does the limit exist? And if it does, what is its value? Okay. So that's one thing I picked up from Manjul, where you put a pause for a question mark, if it's an important question. Okay, so, well, we can make the same guess, right? So let's hope that we can use the Chinese remainder theorems for different primes, for infinitely many primes. And then for each prime, we define this probability that it's square free at P. And so that's just the number of the number of z mod P squared z, number of n tuples in z mod P squared z. You count the number of them where f is non-zero, and you divide by the total number of n tuples. And then using the same method, right, you apply Chinese remainder theorem for all primes up to m, and then you take limit as m goes to infinity. You can prove that this product gives you the upper bound. And again, the difficulty is to prove that this is also the lower bound. Okay, so why is the lower bound difficult? Well, if you just start with a random polynomial f, right, then you don't even know that it will take square-free values infinitely often, let alone any statement about the density. It could just be 0. In the case of discriminant, this is known thanks to the work of Tetlaya. Well, he proved something better. Not just this takes square-free values infinitely often, but it takes infinitely many square-free values. Okay? So there's a difference between them. More precisely, what is actually difficult about this? Well, if you use the Chinese remainder theorems for all primes up to m, then you're overcounting by this amount. You're overcounting by n tuples in the box, where f is divisible by some p squared for some large p. Right? This is the kind of tail estimate you have to do. All right, why is this difficult? This is difficult because, well, each AI can only go up to x. But if f has many variables, and if it has huge degree, then f of a1 of the an can take some very huge power of x. Well, it can be in a range that's very high power of x. So the primes whose square divides it, where did that hand come from? The primes, oh, it's this one, okay. So the primes whose square divides it can also be really big. Okay, and why is that bad? Well, that's because the only thing we know about the problem is this Cp. And Cp tells me what happens in the interval of length p squared. Well, if p is so big compared to x, p squared is enormous. But each AI can only go in a range of x. So what you know about Cp doesn't really say anything in this small range. So that's why the problem is difficult in general. This is the advantage of having 2 slides. Well, it's not difficult in degrees 1 and 2, because in those cases, f doesn't really become too big. The range of primes that whose square divides f can only go up to x, in which case you can just use an elementary method to deal with this. Okay. In degree 3, p can go up to x to 3/2. It's bigger than x, but it's not that much bigger. Okay. But even though it's just slightly bigger than x, Huli needed to use some very heavy analytic number theory machinery to prove this. I have yet to understand his proof. Okay, and that's how much we know, unless, well, it depends on what you believe. If the ABC conjecture was proved, then a result of Granville using earlier works of Elkies would imply that in the single variable case, it's known for any arbitrary degree. For binary forms, so homogeneous in 2 variables, then this is known up to degree 6 due to works of Greaves. And in the multivariable case, Hunan used a different ordering where he fixed the last coordinate and let the rest go to infinity first, and then the last one go to infinity last. Then he can reduce to the single variable case that's unconditional on anything. And then you can apply Granville's result using ABC to finish the problem. So that's what happens in general. Either we know everything or very little. In recent years, there have been some success for some really special polynomials, thanks to works of Manjul. And what's special about these polynomials is that they arise as invariants of some representations of groups, of algebraic groups. The case of polynomial discriminant is one such example. And I will say later why being the invariants of some representation really help in doing a square-free sieve. Okay, so let's get down to the proof. How do we count these n tuples where f is divisible by some large prime square. So to do that, we have to understand how p squared can divide f. Well, there are two possibilities. Either it's for mod p reasons or for mod p squared reasons. Mod p reasons just refer to the fact that you only need to know what the AI is mod p to conclude that p squared is dividing f. In other words, no matter how you perturb AIs by multiples of p, you will not change divisibility. P squared will still divide f. And that's what it means to be mod p reasons. If this fails, if you can change a coordinate by multiples of p that destroys divisibility by p squared, then it's really for mod p squared reasons. Basically, it's just what you expect the definitions to be. So what does this all mean for discriminants? Okay. For discriminants being divisible for mod p reasons means if you reduce f modulo p, then they either have a triple root, a pair of double roots, or worse. Right, so for these polynomials, if you modify them by multiples of p, then it won't change what it looks like mod p. It will still have these singularities, right, and therefore p squared will still divide the discriminant. What does it mean to say it's for mod p squared reasons? So here I give an example where nothing happens for the first from n to the xd n to x squared, and then you have p dividing the linear term and p squared dividing the constant term. If you just look at this mod p, then you only see a double root at 0. That's not enough to guarantee p squared dividing the discriminant. You really need this extra p squared to get p squared dividing the discriminant. And if you modify this last coefficient by a multiple of p that destroy this so that it's no longer multiple of p squared, then p squared will not divide the discriminant. Okay. So because of these three main reasons, either a triple root mod p, a pair of double roots mod p, or this strange px plus p squared case, and they all occur with probability about 1 over p squared. That's why the lambda p in this case is 1 minus 3 over p squared plus lower order terms. That's where the 3 comes from. This is for n at least 4. When n is 3, then you cannot get a pair of double roots anymore. Then it's 1 minus 2 over p squared. And when it's 2, you cannot get a triple root, so it's just 1 minus 1 over p squared. Okay, so why is it important to separate them into mod p and mod p squared case? Well, because the mod p case can be handled really directly. It's sort of geometric, right? So we call this the Ekadel-sieve, originated from the work of Ekadel, Sanak, and finally Manjul. What does the Ekadel-sieve do? What's the key point? The key point is if p squared divides f for mod p reasons, then it should do so for 2 mod p reasons. There should be 2 polynomials, both of which should be vanishing mod p. Well, what's an example for those 2 polynomials? You can take f1 to be f itself, and you can take f2 to be any of its partial derivatives. Obviously, if p squared divides f, then p also divides f, and then the second one is just some simple Taylor expansion. What does independent mean? Independent means that these 2 polynomials, f1 and f2, should cut out the codimension 2 subvariety. Okay, so this basically works for any polynomial f. There is one case where this doesn't work. Okay? It's the case when f itself is not square free. Then, let's say there's a polynomial q whose square divides f, then q will divide both f and any of its partial derivatives. So the variety cut out by them will have this codimension 1 component cut out by q. So that's the one case where the Ekadel-sieve doesn't work. But then you might ask, well, if the polynomial is not square free itself, then why are you asking its value to be square free? Well, that's a valid question, but just keep this in mind. This will come back. Okay, so just a quick sketch about how the Ekadel-sieve work. First, you apply some change in variable to make sure that one of them only involve the first n-1 coordinates. You can do this by taking some resultant. And then you use the first n-1. You take whatever value for the first n-1 coordinates you want. Right? You compute its value under f1. P has to be a prime factor of that. So you use that to get a bound on what the primes P can be. And then you use that bound along with f2 to get a control on what an can be. So that's the basic idea of the Ekadal sieve. Okay, so the more of the story is mod P case can be handled very directly. And we have a way to do this for basically every polynomial f. The mod P square case is where it has to be done in a case-by-case analysis. I say that's the meat of the argument. I guess if you're a vegetarian, you might not think so. Okay, so how do we deal with mod P square case? Okay. So what does it mean to be so from now I'm not going to be looking at arbitrary polynomials, so I'll just be focusing on discriminants. Okay. So for P squared to divide it for mod P square reasons, that means somewhere in your F there's a hidden P square that you cannot break apart. So what we try to do is you want to first find this P square and then you break it apart. So here is that P square. Basically, the example I gave earlier is the universal example. Okay. If you take any monic polynomial of degree n where P square divides a discriminant for P square reasons, then there's a unique double root mod P. You move that point to 0 so that P will divide both the linear term and the constant term. And then in order for P square to divide the discriminant, it turns out that P square has to divide the constant term. So I won't give the proof of this. The hint is basically just looking at using the resultant definition of the discriminant and then see how it depends on the last two coefficients. Okay, so we find the mysterious P square. Now we want to break the P apart. And why do we want to do that? Because we want to transform into mod P reasons. We know how to handle mod P reasons really well. All right, so how do we transform? How do we break up the two P's? Well, if you think about this, you quickly realize that, well, there isn't much you can do. Basically, this is the only transformation you can do to monic polynomials. Well, there are other ways that other things you can do, but that would destroy the discriminant. So what you need to do is, while the space itself is too small to do any transformation, let's try to map it into a bigger space that hopefully has more symmetry, and then use the symmetry over there to go from mod P squared to mod P. Now this is where, but which space? Now this is where knowing that these polynomials are invariants of some representation help. Because that gives you a candidate space. I just map it to the representation. And even better, there are lots of symmetries because there's a group acting on that space. But in general, you have to ask this question. If you just start with any random polynomial that you don't know is invariant of anything, then you have to ask yourself which space I want to map it to. Well, a bigger space will have more points. But we don't want this actual order of magnitude, right? We want to cut down the actual order of magnitude. There are two ways we can do it. The first way is to, well, not map it to the entire vector space. Go to some subvariety of some codimension and then count points in that subvariety. But there's a problem to that, which is, well, it's way harder to count points in the subvariety than it is to count points in the vector space. Well, there's another approach, and that goes back to knowing that your polynomials are invariants of some representation. Namely, you cut down this actual order of magnitude by using a group action. So instead of mapping to points in the vector space, you map to orbits for the representation. And then you count integral orbits using the counting techniques of Manjul. And that's a smiley face. Because Manjul's new ideas on geometry of numbers really changes how we think about orbit counting problems. Before Manjul's work, there were some works on counting integral orbits, Davenport, Halbrand, UK Wright. But those, to do those counting, you have to know exactly what the fundamental domain looks like. You have to know the polynomial inequalities that define the boundaries. In particular, there's no way to do that in an infinite family at the same time. But Manjul's ideas of averaging over a continuum of fundamental domains allows you to basically go from counting very little to counting basically everything. So that's one of, and that's what I what I believe is one of the most important contributions of Manjul's work. Okay, so if counting orbits is doable, what's difficult in this situation? Well, I sort of hidden. The difficulty is defining this lift. And I will say more about why that's difficult. Okay, so I've been hinting at our polynomial being the invariance of some representation. So what is that representation? It's the representation of SLN of n by n symmetric matrices. So you've seen the bigger picture already in Dick's talk, where you had this SLN acting on pairs of symmetric n by n matrices. So over here, you're just fixing one of the symmetric matrix to be A0. This matrix is 1 on the antidiagonal and 0 elsewhere. Its stabilizer inside SLN is by definition SON, and then that acts on the second component. Okay, so more precisely, you have A0. That's defining a split quadratic form of discriminant 1. G is its special orthogonal group, acts on the space of n by n symmetric matrices in the obvious way. Okay, so the invariants of this representation match up exactly to the coefficients of a monic polynomial. Okay, so we can define this invariant polynomial of n by n matrix B by taking, this is basically the characteristic polynomial of A0 times B. I'm studied in this way to look more like what's in Dick's talk. Okay. And then we define the discriminant of this n by n matrix to be the discriminant of its invariant polynomial. Okay, so why this representation? Well, we knew this representation already from earlier works, from Dick and Manjul's work on 2-summer of monic odd hyperelliptic curves, and in Arul and my work in monic even hyperelliptic curves. In particular, we know how to count orbits. Except the orbits we count are slightly more in the compact part of the fundamental domain, where here we have to count deeper in the cusp. But the general framework is there. Okay, so the hard part is defining this lift. So what are we trying to do in this lift? Right, we start, let's define WP to be the set of problem polynomials. Right, the polynomials whose discriminant is a multiple of p squared for some weird mod p squared reason. Okay. We want to define a lift from WP back to n by n symmetric matrices. Lift meaning that if you take the invariant back, you recover the polynomial f. Okay, so, well, why is this in general difficult? Even if you have a representation with the correct invariance. If you remember in Dick's talk, in the case of SLN on pairs of symmetric matrices, the invariants were coefficients of binary n forms. But if you just give random coefficients to your binary n forms, then you might not be able to find pairs of matrices with that invariant, even over R, let alone over Z. So that's sometimes, I guess one problem, one cause for that is that that representation did not come from Wimberg theory. But even if you do come from Wimberg theory, even if there is an algebraic section backwards, that's not going to be our map. Okay? Because any algebraic map will not be able to separate the p squares into two p's. So whatever map we define has to be really clever in separating the two p's. Okay, so let's look at that map. I'm only going to write down the formula when n is odd. When n is even, it's pretty much the same formula. So let's look at the case when n is 2g plus odd. Let's take one of our problem polynomial. Then we know there was a double root mod p, and then moving that double root to 0, we see that f of x plus c has this form where p divides the linear term and p squared divides the constant term. Okay, are you ready for the lift? So here we go. I'll give you 10 seconds to parse this. Okay, I think that's 10 seconds. If you haven't figured out why this works, if you haven't understand everything about this, don't worry. This matrix will appear in many slides. So this is supposed to be a lift, meaning if you take the invariant back, you should recover f. The plus C A naught at the end is just to deal with the f of x plus c. And so if you just take this big matrix, then its invariant should just be that polynomial out there. Okay, so here you see the separation of the two p's, right, in the two different corners of the matrix.
Can I ask a quick question about the formulas? Is the point that we sort of start with some sort of more something that makes sense without taking into account p, and then we sort of conjugate by p and pull out p squared and bn and p from bn minus 1, and that throws the two p's up into the top right and the lower left? Or
sorry, were you asking?
I'm just trying to sort of summarize in one sentence why it should sort of vaguely look like this. Is the point that you have there's a p in the top right and a p in the bottom left?
Yeah.
Do those somehow come from conjugating to get rid of p squared and bn and p and bn minus 1?
Yeah, that's yeah. So basically, we had this algebraic lift from Wimberg theory. Yeah. That's going to be this, but they are rationally equivalent, but not integrally equivalent. And what you were saying about conjugating by 1 over p is something that's in Q but not in Z. Yeah. So that, yeah. Well, yeah, retroactively. Yeah. But in Dickstock, you had this this pair of matrices coming from an integral point on the hyperelliptic curve. And there you had these two C's, right, at the corners. This is very similar to that. I think this is probably where it came from in the first place. Okay, so where did that, it should appear here. What happened? What if I do this? Oh, okay. It just reached. Okay, so, well, I'll put this all up here. Okay, so we've defined this lift. Does it work? Okay, our goal is to go from mod p squared to mod p. Okay, so here's the map. Does p squared divide the discriminant for mod p reasons? If it doesn't, then what you've done is sort of useless. Well, it's not useless. It's a correct step towards it. Okay, so the discriminant, remember, that was defined as the discriminant of the invariant polynomial. And the invariant polynomial had this p divided in the linear term and p squared divided in the constant term. So the question here is, if you perturb the entries of this matrix by multiples of p, will p still divide the linear term? Will p squared still divide the constant term? Well, one of those two questions is really easy. P will still divide the linear term, because p divides anything always for mod p reasons. What's the constant term? The constant term is the determinant of this matrix. So basically what we're asking, does p squared divide the determinant for mod p reasons? If you change the coefficients by multiples of p, will p squared divide the determinant? Well, I've given away the answer. It's not, right? You can take out a factor of p from the first column. When you do that, the top left coordinate might just become a 1. And then there's no way to take out any other factor of p from that matrix. So it doesn't actually work. But why am I spending so much time on this? Because it almost works. The only problem is that top left corner. If that corner is not allowed to change whatsoever, if that coordinate is just fixed to be 0, okay, if you're only allowed to change the rest of the matrix, then you can take out a factor of p from the first column, right? That entry is still 0, and then you can furthermore take out a factor of p from the first row. Yeah, so that number should be p squared. Yeah. But saying it's p squared, that's no longer a vector space, so let's just make it 0. Okay, so in other words, let's not look at the entire space V of symmetric n by n matrices. Let's look at a subspace of codimension 1, where the top left corner is 0. Then, if you only allow coordinates inside V naught prime to change, right? So going to a smaller space means there are less you can change. So there's more chance for p squared to divide the discriminant. And then p squared will divide the discriminant for mod p reasons for the smaller subspace. Okay, so to summarize, our first lift doesn't actually work, but you immediately see what the problem is, and then you just throw away that problem by saying you are not allowed to do it. Okay, now, we sort of cheated here. we had some earlier works on two summers of Jacobians, and for us, we knew that it's more natural to not just force that one entry to be 0, but force that entire block, that entire G by G block to be 0. Okay? So we're going to define V0 to be the subspace of n by n symmetric matrices where the top left G by G block is identically 0. Let me see if it works if I put the next slide over here. Yeah, okay. So the significance about making sure that block is O0, well, A0 also has that block O0. A0 is a matrix that's only got ones on the anti-diagonal. Okay. So this subspace XG, defined by taking the space spanned by the first G basis vector, that's a common isotropic subspace for the quadrics A0 and B, and any matrix in this subspace V0. And we know quite well the theory of tensors of quadrics and the set of maximal isotropic subspaces contained in the base locus. So that's why it's more convenient for us to define this even smaller subspace. Okay, so the subspace is smaller, but the group no longer acts on it. It's not going to serve that block of zeros, but the subspace, the subgroup does act on it. The parabolic subgroup of G that fixes this top left block will act on V0. Okay, so just a more concrete description of what this parabolic subgroup look like. You just have a 0 on the top right corner. Okay, so our lift was a map to V of R, but it's really to V of Z, 1/2 times V of Z. Okay, so our idea was to then count GZ orbits on 1/2 V of Z. Okay. Well, it turns out that we don't want to do that, but what we do instead is to count G0 of Z orbits on 1/2 of V0 of Z. So we go to a smaller representation. Okay. Anytime you want to count orbits, you want to know what the invariants are. So what are the invariants? Have you introduced anything more? Okay, so all the original invariants are still invariants. They were invariant for the bigger group and therefore also for the smaller group. But turns out that there's one extra invariant. We call it the Q-invariant. It's called the Q-invariant because, one, we were running out of letters, and two, this is really cute. So we just call it the Q-invariant. Okay. And so what is the Q-invariant? The Q-invariant depends only on the top right in G by G plus 1 block. Okay. If you remember, V0 was this subspace where the left G by G block is 0. So I'm just going to take the top right G by G plus 1 block. Okay, so what am I going to do with it? I'm going to use it to define a map from V0 to 2 tensor G plus 1. So that's the space of pairs of G by G plus 1 matrices. The map takes any matrix B and you put first to A0 top. Okay, so this means you take the top G by G plus 1 block of A0. It's fixed. It doesn't depend on B. Okay? And then the second component is the top right G by G plus 1 block of B. So this is just a map. It's not of anything. There's no structure to it. Maybe there's a group invariance, but apart from that, there's nothing. Okay, so what's the Q invariant? Well, we take the hyperdeterminant of this 2 by G plus 1 matrix. So that's an SO2 by SOG by SOG plus 1 invariant. We take its hyperdeterminant and pull it back via this map. That's the Q invariant of a matrix in V0. Okay, that probably doesn't mean anything to you. We're too modern to remember what the hyperdeterminant is. Okay. The key point is, if you take your lifts and you compute the Q invariant, it turns out to be plus or minus P. So let me again go back to the lift. Right? So there was a plus C A0 at the end, but because of SO2 invariance, you don't have to worry about that. Now you take the top right G by G plus 1 block. Now notice that doesn't depend on F. It's just a bunch of P's and 1s and 0s. Okay? So you just plug in the formula for the hyperdeterminant, which in this case is a very explicit formula. And then it outputs plus or minus P. So this is one of the most important properties about this lift. Okay? So first, being a lift means if you take the invariant, you recover F. And second of all, you recover P by taking the Q invariant. So somehow these two invariants recovers the F and where the problem is. Isn't that cute? Okay, so I said there was a relative invariant. What does that mean? That means if you take an element in G0 and you act it on B, it doesn't fix it, but it multiplies it by a determinant of gamma 1. But I still call it the Q invariant because at the end of the day, we're looking at G0 of Z orbits. And for G0 of Z orbits, up to sign, it really is an invariant. Okay? The determinant can only be plus or minus 1. Okay, so we have this extra invariant that recovers P. Here are some fun facts about this Q invariant. The first fun fact is basically telling you that counting G0 Z orbits and counting GZ orbits are pretty much the same. Okay. If you take two elements in V0 of Q, so two n by n symmetric matrix with top left G by G block 0, if they turned out to be G of Z equivalent, okay, and if their invariant polynomial is irreducible over Q, then they're actually G0 of Z equivalent and therefore have the same Q invariant up to psi. So this property, this requirement of their invariant polynomial being irreducible translates to the condition that there's a unique G-dimensional common isotropic space for A0 and B1, for example. And by using that uniqueness, you can show that any element of G of Z that takes B1 to B2 has to lie inside G0. But assuming things are irreducible is no harm. It happens 100% of the time. Okay, so that's the fun fact number 1. Fun fact number 2 says, well, Q is a polynomial only in the top right G by G plus 1 block, but if you view it as a polynomial in the coordinates of B0, then its square turns out to divide a discriminant as polynomials. Okay. Now you look at fun fact number 2 and then you say, wait a second, that's not fun at all. Right? Because remember what we were trying to do. We're trying to go from mod P squared to mod P because we can use Ekadov sieve to do mod P. There's one case where the Ekadov sieve doesn't work, and it's the case here where delta is not square free as a polynomial. So we're sort of screwed. Maybe I've just wasted 40 minutes. Okay, and then you think about this for a little bit, and then you realize, what are we trying to do? We're trying to count these polynomials whose discriminant is a multiple of P squared for some strange mod P squared reason. We have identified what that problem is. The problem being that if you take the lift, the Q invariant is really big. The Q invariant is P. Okay. So let's just forget about the Ekadov sieve. Okay, let's just count GZ orbits inside 1/2 V0 Z that has very large Q invariant. Q invariant bigger than M, for example. Okay. And that's something we can do, thanks to the counting machineries of Manjul. Okay, so a recap of the strategy. Our goal is to square free sieve. So step 0 is to break up into mod P and P squared case. Mod P case, you use the Ekadov sieve, and that just kills it. For the mod P squared case, you first have to identify where that hidden P square is. That's usually not very hard, usually a lemma. And then the hard part is to choose the new space to embed your problem polynomials into. And in some sense, 2 and 3 are sort of the same problem. You want to find this new space, and then you want to find a lift from polynomials to elements in the space, or from polynomials to orbits in the space. Sometimes the most obvious lift doesn't work, for example, from Wimberg theory, and then you have to make some modification to make that actually splitting apart the two P's. And then it's still not going to work, right? In our case, we realize that there's a top left 0 that we have to deal with. So you make some necessary modifications to really go from mod P squared to mod P. And maybe in the process, you've introduced more invariants, like the Q invariant. Okay. So you use the new invariants, and you count in a bigger space, and then you win. Okay. So I put number 2 in red because we don't know, in general, if you're just given a polynomial, when can you do this? maybe for some polynomials it's just not possible. So that this is basically completely open to us. We don't know what to do in general. It's sort of lucky that we can do it in the case of discriminants. Okay, so that's a sketch of theorem 1, square-free discriminant. Okay, so for the remaining 10 to 15 minutes, I want to talk about the applications to counting number fields. Okay, so our results give the correct proportion of polynomials with square-free discriminants. Okay. How are we going to use that to construct different number fields? Well, we're going to be looking at the rings generated by them, Zx mod f of x. We'll show that 100% of the time, these rings are distinct. Okay. Well, if we also know they have square-free discriminant, then these rings in the ring of integers will tell you that the fields are also distinct. Okay. Should always talk about fields at the Fields Institute. Okay, how do we distinguish these rings? Well, we can do them as lattices in Rn by using all the Archimedean embeddings of the field. They're not just a random lattice. They came with a power basis. They were monogenic. Right? If you take the image of x in a quotient, then there's a basis given by 1, theta, theta squared, up to theta to the n minus 1. And you can ask whether this basis is special, whether it's Minkowski reduced. So Minkowski reduced means at every stage, this is the shortest vector, so that if you take the previous ones, it can be completed into a basis for the lattice. Well, they're usually not Minkowski reduced, but they're close. Okay, so let's start with a monic integer polynomial with no x to the n minus 1 term. Okay. We say it's quasi-reduced if the power basis is Minkowski reduced after some upper triangular transformation, or lower triangular, depending on your viewpoint. So this just means there exist monic polynomials of each degree such that 1, and then the monic polynomial of degree 1, the monic polynomial of degree 2, and so on. That's a Minkowski reduced basis. Okay. In theta, yeah. Somehow, by taking out the x to the n minus 1 term, this is the best you can ask. Okay. Most lattices have a unique Minkowski reduced basis. So we'll say a polynomial is strongly quasi-reduced if the lattice has a unique Minkowski reduced basis. If in addition that f is already quasi-reduced. Okay, so what do we prove? First, we prove that if you are strongly quasi-reduced, then you will have distinct rings. Okay, so if G1 and G2 are distinct, irreducible monic with vanishing x to the n minus 1 term, and if they're also strongly quasi-reduced, then the rings they generate are distinct. Okay, so the idea here is basically any ring isomorphism will have to send a Minkowski reduced basis to a Minkowski reduced basis. And it has to send basically theta for G1 to some theta plus c for G2. And c has to be 0 because none of them have any x to the n minus 1 term. The second lemma is, well, strongly quasi-reduced is pretty much an open condition. 100% of these polynomials are quasi-reduced, are strongly quasi-reduced. Okay. So 100% with respect to this height where you give each ai degree I. Okay, so these two lemmas is already telling you that 100% of these polynomials will give you distinct rings. And then we use our result on square-free discriminant to say that distinct rings also imply distinct fields. So a positive proportion of these special polynomials, when ordered by this height, have square-free discriminant. Now everything I've said before has an x to the n minus 1 term, but the proof works exactly the same way. You don't have to change anything. It just works in this special case as well. Okay, so we've got these 100% having distinct rings, and this positive proportion of them having square-free discriminant, and therefore the fields will be monogenic SN fields, and they will be distinct. So some numerology. If the height is bounded by x to the 1 over n times n minus 1, then because the discriminant is weighted homogeneous of degree n times n minus 1, you see that the discriminant is bounded by x, or some multiples of x. Now, how many of these integer polynomials are there with height bounded by x to the 1 over n times n minus 1? Well, a2 can go up to height squared, a3 can go up to height cubed, an can go up to height to the power n, and you get this x to the 1/2 plus 1 over n. So that's the number of monic polynomials, and then you multiply by the correct density, something about 35.82%, you get a constant times x to the 1/2 plus 1 over n, distinct monogenic SN fields. So why do we believe that this order of magnitude is correct? Because we believe that the converse of the first statement is true 100% of the time. If discriminant is bounded, then the height should also be bounded. Okay, so I will end with this picture of Manjul taken at the time where we first came across this Q-invariant, which was taken in a train in Germany on our way to Oberwolfa. All right, thank you very much. Sorry, can you repeat the question?
Some invariant Q exists for parabolic.
There should be. Whether the Q invariant exists for some other Wimberg representation. I think if you go to some subspace and then where the discriminant is no longer square free, then whatever that's whose square is dividing it should be an invariant. So that should be the new Q invariant. But which subspace do you go to so that discriminant becomes no longer square free? I don't know. They should exist, should correspond to, from geometry, there is this common isotropic space, or when the elliptic curve, when the p covers of the elliptic curve has a rational point. Yes.
Is this lower bound for monogenic SN field now also our lower bound for SN field period?
No, we can get it to 1 over n minus 1. that uses general polynomials, not just monic. Yeah, the previous one was from Ellenberg Venkatesh, where this is 1 over n squared. Just a tiny improvement.
Can you say why you believe the converse one holds 100% of the time?
Manjul, you want to answer this question? Whether the converse?
When you have a discriminant polynomial, like lots of terms that you're adding up something small, when x and most things are small, the chance of that cancellation. Usually when you have some bunch of terms, size of some is usually going to be about the size of the biggest term that's there, and the chance that it's going to be lower is rare. So if you're discriminating with the curve, the reason why you use the number third, you're getting discriminated to be the same but at the third height. Because you don't expect minus 4 is going to be minus 27b squared, so maybe you have this conspiracy to make it smaller in size than the original. So it's an effective positive.
So you say positive proportion.
Yeah.
Okay. And just for the same reasons you feel that way about any polynomial.
Once they're higher,
Does this follow from ABC?
Sure.
Sure. Yeah.
So I have two questions. One is, in this theorem, you said A 1 to 0.
Maybe I should count. Sorry, I want to get rid of this picture.
Right, so in this theorem, you said A 1 to 0, and you said the argument kind of works the same way.
Yeah.
Is the same true if you say fix any finite number of coefficients?
Yeah.
Everything works. Maybe not.
I think it works for any one of them.
Okay.
Yeah.
The other question. What can you say about distinct values here?
That's a good question. We haven't thought very hard about it. but we couldn't get a bound that's better than yours. Really? X to the 1 over minus 1.
You couldn't get any better than that with this method? Wow.
Well, we'll think about it. Yeah.
One ought to be able to get something close to this, I would think, no? Certainly something that, I mean, certainly X to the epsilon, where epsilon is something that
doesn't depend on n. Yeah, that's something that we're thinking about. Yeah. So far, it's not a no.
A similar kind of analysis with Q-free determinants or power-free determinants?
Well, square-free, but in the case where you cannot do square-free, then you would have to separate the case to mod p square, mod p cube reasons. Mod p case, you can just do it again. I'm not sure about mod p square. I think there you already run into problems, and then you get even harder mod p cube. So I don't know in general.
The discriminant is always 0 or 1, not 4.
That's right. It's always a square, not 4.
Yeah.
That's a polynomial.
Yeah, it's true. I do understand. Anyway, as an alternative to consider things here, consider fundamentals. And instead of some of these properties, for instance, if we're going to have fundamentals there, any of the answers related to keep methods,
I think that only matters at 2. Yeah, and you still have all of these infinitely many primes to deal with. That's the hard part in the lower bound.
maybe the related question I should ask is, does everything work the same if you forget finite dimension?
Yeah. Yeah. Even at infinite places. As long as it doesn't make the problem trivial, that it can no longer be square free for local problems. That's just an artifact of the counting argument. It works for any congruence conditions.
Any other questions? Okay, we're going to have a 10-minute break, but let's first thank our speaker.